Good morning, Srini. How was your day? Okay, what is meant by resistor or conductor? Okay, tell me. What is meant by resistance of a conductor? Yep.
The potential difference across conductor over the current in the conductor itself.
Current flowing into the conductor. Okay, good. How about resistivity?
Resistivity of the metal is the resistance of the unit length of a piece of a metal that has a unit cross-sectional area.
You say resistance of a length.
They say resistivity of the metal.
Okay, resistivity of metal is what?
Resistivity of the metal is the resistance of a unit length of a piece of a metal that has a unit cross-sectional area.
Correct. It must be unit length, unit cross-sectional area. Or you can remember the formula better still. How about temperature coefficient of resistance? Cannot, then write down the formula lor, and then tell what the symbol stands for.
Yeah, R minus R0 over R0 times.
That is not resistivity, that is the resistance.
You're asking temperature, right?
Coefficient is this formula. And then tell the examiner what the symbol stand
John,
for.
I'm telling you.
That's all you need to do. Right? Write down the formula. If you don't want to write in words, then tell the examiner what is R. R naught is the resistance at reference temperature. Then R is the resistance when temperature increase. Is the change in resistance per unit reference resistance per unit change in temperature. And sorry, this one is reference temperature is T naught. Okay or not?
Okay.
Either you write down.
Oh, and usually if you're not sure the definition means, can write formula.
You write the formula, but you must tell the examiner what does each of the symbols stand for.
Oh, I always thought like definition means like you have to write in words only.
If you can remember words, will be better, but I don't think it's wrong to write in that one and then tell the examiner what does it mean, each of the term. Right? Or this one, change in resistance. That's the change in resistance per unit reference temperature, per unit reference temperature, per unit change in temperature, per unit reference resistance, per unit change in temperature. Okay, you should be able to sketch the graph. That's how the graph
go back
looks
again,
like.
Yeah, okay, sir.
Right? That's how the graph look like. Sketch the graph to show how the resistivity of metal varies with temperature. How would you deduce the temperature coefficient or resistivity for graph? Right? See, that's why they ask you to define. You define that, then you can see this is a change in resistance. This is a change in temperature. So that is your gradient. So it is a change in resistance per unit. That is what you define. So it's just a gradient divided by R naught. Can?
This one just memorize only lah.
This one got meaning one. I can see from here you memorize this one. Not everything memorized. Right? Memorize this one. And then this is the height. This is the height. This is the x distance. That's the x distance.
Oh yeah, like in the definition itself.
So this one is just a gradient. Gradient divided by R naught. You try to memorize everything, you can't know how to get it. No, does it mean? We see so many formulas. Okay?
Okay. Okay.
Okay, part C. A strip of silver has a dimension 1, 5, 20 millimeter. The same potential difference first applied in the vertical J direction. That direction is the current. Because that's where the potential is applied, that's where the direction of current. Which direction of the applied potential difference yield a greater current in this piece of silver? Use a macroscopic model of current to explain your answer. Okay, direction of J, right? Explain. Right? They ask you which direction. Direction J gives a greater current. Then they ask you to use this formula to explain. Why? Cross-sectional area is the largest. This part, cross-sectional area is largest. They will draw for you to see. Other part is smaller. So there's more. Since cross-sectional area is larger, more charge carrier are available for conduction. Okay. Okay now. Okay now.
Okay.
Then a piece of doped silicon has the same dimension as the silver piece. The same potential difference is applied separately in the direction H. That is the direction H. And then across a piece of doped silicon, right, apply to silver and apply a doped silicon. Each piece of material has a smaller current. Give qualitative explanation. Qualitative, you have to explain without using formula, without using calculation. They give you density of conduction electron in silver, density of conduction electron in dope. So what is the answer? Yep. Any idea? See, yeah, ask you to use that formula. So use that formula to explain.
Oh, qualitative means explanation without formula lah.
Not too much formula lah, but roughly you must have an idea that that is the formula you are using to explain. Don't have to use a lot of maths. Don't need to calculate value. That's why it means qualitative. Quantitative, then you have to calculate. It's mainly maths. Can.
1 minute answer. Current is smaller in the semiconductor because the number of charge carrier is very much less than in silver.
Correct. Yeah, you can see from here they have given you that. So a piece of silicon would have a smaller current as the number of charge carrier is smaller than a piece of silver. Okay, good.
Yeah.
Okay. Okay, I think we will stop here. Any question you want to ask? Anything else from electric current you want to ask? Not, let's go to our
No, let's go
DC.
chapter 4, Jeff.
Okay, let's go to 15 then. Have you done the checkpoint question? No point in going too fast, right? It's better each topic you are well versed before we go further. Okay, checkpoint 15, 15.1.
Yeah, number
Can you
one
do all of
only I
them?
can. I could only do number one.
Okay, can do number one, so we won't bother about number one. Number two, a piece.
Sir, go back again, sir.
I thought you say you can do number one.
No, I just wanted to see something.
Just draw a
Okay,
rough
sir.
picture so that you know what is happening. Internal resistance, external resistance. Okay, just
Okay.
memorize the formula and use the formula. That's all. Okay,
Okay.
number two also the same thing. A source of EMF. That's the source of EMF. Has an internal resistance R. Right? Draw a picture. Draw a picture. Even they don't give you, draw a picture that can understand. You can picture what's happening. Use to light a lamp. R is your lamp. Find in terms of R and R the fraction of the power supplied by the source to light up the lamp. Okay, we have done that. Basically, it's just efficiency. Right? Power supply. Sorry, power output. Yeah, I squared times R. Power supply. Supply is this. You must include all these two resistance. Right? Because all the power is lost in these two resistance. The small r and the big R. That's why I squared times R plus R. And power output, this is your fraction. No? Power output over power supply is called the fraction. And you can cancel the I square, here you got R over R plus R. That's all. You didn't study. Okay, got what you want?
Oh, that's it.
That's all. You need to put an effort to learn. I can't learn for you. I can only teach you.
Okay. Number three, sir.
EMF of a cell is 1.5. That's EMF. Internal resistance 0.5. Calculate the power supply to the external resistance. That's the external resistance. Right? So calculate the current first. So many ways to calculate, not only one way. Right? There's the EMF. I R plus R. Then calculate your I. E is 1.5. 0.5 plus 2.5. That's your R plus R. Then you get your current. After getting current, you want power supply to the 2.5. This one. So it's I squared times R. Put your value in. Okay. You can use formula, but I just try to not to use too much formula. Right? The limited, the basic one that you need to know. What's the resistance of the external resistor when the power supply from the resistor is maximum? Yeah. What's the resistance of the external resistor when the power dissipated from the resistor is maximum? Yep. What's the answer?
0.5.
Good. This is memory work. You must know. When they are external resistor equals internal resistor, then you have maximum power dissipated. Dissipated means loss. Loss as heat. Okay.
Okay.
Got number 4 or not? No. Let's
No,
go to.
there's only 1, 2, 3.
Okay. Let's go and start with our Kirchhoff's law. Okay. Let's go to Kirchhoff's law. Right. We still got 3. We will try to cover Kirchhoff's law today. Okay. basically your formula is very vague. Right? State and apply Kirchhoff's law. Very vague. You need 4 hours. Okay, page 104 in your book. Right? This is your simple circuit. A battery, a lamp or resistor, plus a switch. Simple circuit. You must have a source of EMF, a resistor. So we are not going to look at simple circuit. We are going to look at more complicated circuit. So we call it network. Well, you can doesn't have to have one light bulb. You can have 2 light bulb, resistor in series, or I can have resistor in parallel. Like here, complicated. So you must know how to calculate. Right? Or we have a network, right? Complicated network. You should know how to calculate that. So these are just for your info. You don't need to know. Only if you are going to do engineering or physics in university. Right? There's an old symbol for resistor. This is a new symbol. And usually this is more common resistor that we use. Partly because it's cheaper.
Wait, R2 is an old resistor.
The old symbol. Old symbol.
Okay.
This is a new symbol.
Last time they used.
Rectangle. Last time.
Okay.
There's your nichrome wire. Nichrome wire is more commonly used because the resistor is larger. Okay, I need this for your info only. Okay, row of resistors provide a path or divert the flow of current. Reduce the sum of current to the desired value. Whatever current you want, you just put the resistor in to reduce the current. Okay, let's go to Kirchhoff's first law or Kirchhoff's current law. That's my symbol. Kirchhoff's current law. Right? It applies to at a junction. At junction there. You can have a power supply there, current flowing in, current flowing out, current flowing out. So Kirchhoff's current law, right? That's why I call KCL. The sum of current entering any junction is equal to the sum of current leaving the junction. Right? This is just a water flowing in equals to water flowing out because none is leaked out, none is lost somewhere. Right? That's my symbol for it. Sum of current equals to 0. It's a conservation of charge. That means the charge flowing in must be equal to charge flowing out. It cannot disappear.
Oh, that's the mere Kirchhoff law.
Kirchhoff's current law, first law.
Charge going in equals to charge going out.
Yes. So charge going in is okay. So total charge flowing in equals to total charge flowing out. That's all. Okay, let's solve this question. Apply solving the problem. Kirchhoff's current law. Sum of current equals to 0. So it means
because they are
that
balanced.
going in, we take it as positive. So it's I2 plus I3 that's going in. Going out, right? I1 plus I4.
Yeah, they are balanced lah. Sure.
They are balanced. Or we can take these two, I1 plus I4 to the other side. So we get equals to 0. That's what the sum tells you. That means
you can minus the I2
this one you
and
must
I3
choose. Right? Taking going in as positive and going out as negative. Or the other way around.
Yeah, you take
your choice.
You take I2, I3 negative also still correct, right?
Yeah. It's just a matter of taking it to the other side as well. So it's your choice.
Okay.
You must take in one direction as positive. Going in is positive, going out is negative. Okay, what's the answer for this one?
Okay, this is fun. Wait, I1 plus I2 plus I3 equals to I4 plus I5.
Okay, good. That's all. That's your Kirchhoff's first law. How about this one?
Go back again. Okay.
How about this one?
What is the value I? Okay. How about this one? Che, go back again, Che, can sorry. Okay. There will be a midpoint one. Okay, go on. Go to the next question, Je. 6a plus I equals to 8a plus 5a. Is it
So what's the answer?
7? Is the answer
What?
7?
How to get 7? 6 plus 5 minus 8. You add those going in minus those going out, then you get your answer.
Oh yeah. Okay. Wait, what? 5 plus 6 equals to 8 plus I. Yeah.
Yeah, that's all.
No, but the other graph was like more easier to analyze. This one like a bit
You won't have
tough.
simple graph. Simple is to have you understand. After that, you need to apply into more and more difficult situation.
No, but that one, right? The before one, at least they show like they connect each other, then the other side opposite.
I
This one
know.
like a bit.
You must learn to solve basic one. After that, go to solve more complicated one. You don't expect simple one to come out. Occasionally, maybe simple one. Okay, Kirchhoff's second law, or sometimes it's called Kirchhoff's K voltage V
voltage law.
law L KVL. In a closed loop, apply to a closed loop. The total EMF equals the total PD drop across the component. Or write in equation form. There's the total EMF in the closed loop. There's a total PD drop. Add them up. Or usually I will write voltage source PD drop, or sum of EMF equals sum of PD. Okay. It's a conservation. Second law is a law of conservation of energy. We show it a while. In fact, we have been using that so long already, a few times already.
Wait, so basically, go back again. So basically, Kirchhoff's second law is just EMF equals to potential difference. That's it.
Yeah.
Oh, it's like energy cannot
Energy
be
supply.
energy can be energy can be conserved. It cannot be destroyed, right? Something like that.
Yep.
Conservation of energy,
It's
something
supply.
like that.
It must be lost somewhere. It cannot disappear. That's what it means. Conservation of energy. Kirchhoff's second law is known as the voltage law. It gives a relationship between voltage drop around any closed loop in the circuit, closed loop, voltage drop, and the voltage source in the loop. So it's voltage drop and voltage source. The two are related. The total of these two quantities are always equal. Like here, that is the source, this is the voltage drop. So we'll be using this formula. That's your source, V. Then we just add one, V1, V2 plus V3. Okay. That's for your series formula we'll be using later on. Note.
Take over again. Okay, just 1 minute. Open loop, no.
We won't bother by open loop. You just know how to apply closed loop. Identify what is a closed loop.
So that means they campur all the total voltages lah. That means.
Yeah, we'll be looking at that. We'll be looking how to apply the law.
I thought the other one was EMF equals to potential difference.
Yeah, so the source of EMF, source of PD drop, right? Or we have shown previously.
Got
source of EMF,
either one lah.
And then the PD drop in the three resistors.
Depending on the question.
That one stand for, it's a Greek alphabet capital letter sigma. Stand for sum of. Remember, it's apply Kirchhoff's voltage law applied to a closed loop. So this is a closed loop. This is a closed loop. That's your V1, V2, V3. Okay, what is mean by closed loop? Is this a closed loop? Yeah, this one?
No, it's not.
Why not a closed loop?
Because the outer one is not closed.
What no outer one not closed? What do you mean? It's a
Okay,
closed one.
look at the left side.
Yeah, left side doesn't matter. It's still closed one. Don't have to work.
Oh, that means the outers one don't have some voltage or something. That's why. Can.
Don't have voltage is a criteria. It must have a voltage source. It must have one or more voltage source. Then you can consider a closed loop. Okay. How to work? Doesn't work. This one doesn't work at all. No current can flow. Right? So it's not a closed loop.
Must
You must
have
have a
batteries.
voltage source. Okay, 10 minutes time, we have to change to another Zoom. Okay. So this is a closed loop. This one is not a closed loop. Right? This is not a closed loop. This is a closed loop because this one no voltage source. Second condition.
Hey, go back again. Yeah, that's why I told you last second one not a closed loop lah.
Yeah, must be able to tell me. That's why you say correctly, no power source, no voltage source. Then that's how you identify it.
No, because the outer one no voltage source. That's why it's not a
no voltage source. That's why it's not a
lah.
closed loop.
Oh, okay. Yeah, that's a closed loop. Okay.
Right? Second condition, a complete path for current to flow from any point around the loop and back to the point. Right? Where it starts from a battery, the current must flow back to the battery. That's what I mean by a closed loop. So is this a closed loop? Yeah, you got a source.
Wait. Yeah, it is a closed loop.
Is it a closed loop?
Yeah.
Okay, be a closed loop.
The potential difference.
Current cannot flow. Current cannot flow. How to be a closed loop?
Oh yeah.
It must be a complete path
they
for
have
current
the
to
other
flow.
criteria.
It must be a complete path for current to flow. So it's not a closed loop. Current cannot flow. Right? And remember, it's a law of conservation of energy. We will show in a while. Okay, how many closed loops are there?
How many closed loops are there? Okay, 1 minute.
Remember, it must be a closed loop where the current can flow. It must have a battery. Then it's called a closed loop.
There's actually 3.
3, are you sure?
Yeah.
Not 2 only.
3, right?
I ask you, right? You must be sure yourself.
Yeah, 3.
You are better than my student.
Correct or not?
They will always say 2 only. Okay, let's go.
So it's 3 or 2?
3 lah. You already got it correct.
Oh yes.
You must be confident yourself. Right? This is the
first
one.
Yeah lah.
The first one. This is the first one. That's the second
because
one.
There's actually because the AB CE one there's actually 2. Like they said, it's
then,
like separate but it's together lah.
That's the third one. Yeah, that's the third one. Don't bother about this one, the center there. That's all. That's the third one. Correct. Good. Okay, I think we
go back again.
We will finish off with here and then go to the next.
Okay. The number 1 you circle is which one again?
Number 1 is this one.
The whole thing. Yeah, just want to be sure.
This is number 1.
Okay, that's number 1. Number 2.
Number 2 is this one.
That's number 2. Okay, number 3 is which one?
Number 3 is the whole loop, external one.
Oh, you champo lah.
Just forget this one. Forget this one. So it's the whole thing. Right? The whole thing. From here.
That means you include 2 ohm plus 2 ohm only lah.
So you
there's only
forget
4
about the
ohm for
4
the
ohm
third
there.
one lah.
Forget about the 4 ohm there.
Yeah.
That's the last one.
Then you take the other 4 ohm lah.
So basically, you just need to know which two of the three you want to use, and then apply the first law at a junction. That's the junction, C and D. Okay. Any comment?
No, I kind of like to study Kirchhoff law. It's quite fun.
Okay. You can try some of the question there. I think I have given you in the book there. In the exercise, I can try that while I start a new Zoom. If you want, you can take a
Okay.
5 minutes break or do the work.
Let's take 5 minutes lah. Or
Okay.
just start a new link fast lah.
Yeah, I'm starting a new
Waste time.
Zoom. Okay, you stop here.
Okay.